Okay, so hello everyone. My name is Henrique. I'm a computer scientist from Brazil, and today I'll be talking about evolutionary coding agents and a bit about my work in code evolve and also with some other frameworks related to sort of the evolutionary search and using large language models as tools for creating new solutions and stuff. So a brief overview of what I want to sort of talk about today. I'll be giving an overview of evolutionary coding agents themselves and evolutionary search. This might be a bit redundant. I guess most of you in the crowd already know a lot about this, but I figured it would be a nice thing to level out the field. Then I'll talk a bit specifically about code evolve and our experiments using some models, and more specifically about why I think this whole evolutionary search approach for large language models is a good way of not only obtaining better results for certain problems, but also sort of enhancing the capabilities of open source models.
Enrique, my apologies.
Yeah.
Trying to use the audio of the TV, so it's a bit louder. People can hear you. A quick check. Were you able to hear Enrique all right? Yeah, also the last row? Okay. Then we're just going to run it from the laptop. Sorry about that, man. If you could.
No, it's fine. You want me to restart, or can I just take it from here?
It depends on how comprehensive your slide is. Let's just do this again. Actually, I think if you just go through this summary of contents quickly again, we should be all good.
Okay. So going back, I'll briefly talk about evolutionary coding agents just to sort of level out the field, and then I'll talk about code evolve and some experiments we made using Gemini and Qwen, and then finish with some thoughts and next steps I think it might be good for the field. So, okay, before starting, a bit about me. I currently work as a research scientist at Inter, which is a really big Brazilian digital bank, and also finishing my master's in computer science. And I got into this whole algorithm discovery thing by working on code evolve and also contributing to open evolve, which are frameworks you might know. And together with my co-authors on the right here, Fabrício, Leandro, and Diego, we've been working on this for over a year now. And sort of the team there is sort of collaboration between different universities, and we focus more on NLP, representation learning, and recommender systems. Okay, so to the talk itself. So the idea of evolutionary algorithms, not going to go into too much detail, but genetic programming has been around for decades, and the sort of evolutionary loop that we're talking about was popularized in the 90s by the works of John Koza. And the idea is I have some sort of function I want to optimize, so this sort of like an optimization scenario. I can think of solutions to a certain problem, and I can evaluate how good the solution is as a sort of a number. And the idea is I might have some initial guesses. So this is a calculation initialization on the figure on the right. And the idea is to iteratively try to generate new solutions in a way that mimics evolution sort of in the real world. So, I can sample some parents, sample some solutions from my set, and then I'll apply the two main variation operators, which are crossover and mutation. So crossover is essentially I have two parents, I'm going to mix them up to create a new solution. And mutation then just introduces some random noise. And the way you do this varies, of course, according to each algorithm and how exactly, which kind of noise you want to introduce. But it's sort of the main force that generates new solutions. And you can repeat this a couple of times to generate a new generation, and evaluate them according to some fitness function. And if that's okay, if you want to, either your budget has finished or you attained a certain fitness threshold, you can stop the algorithm, or you can just keep repeating. But the idea is I'm going to iteratively generate new solutions from the population pool itself, but also according to some random noise. Okay, so this is pretty classic stuff. And the solutions up here, I think it's pretty critical to understand that we're representing programs. So you can think of like a Python code or whatever. But the idea is that classically, the way you would represent these programs, the figure on the right shows an abstract syntax tree, which is sort of like a pretty classical data structure. And the figure actually shows something called subtree crossover. So the idea is I have two parents represented as trees, and I'm going to choose some subtree of the parents and combine them to generate new children. So this works fine for many problems, and genetic programming has been applied successfully many times. But it's kind of hard when you have large code bases and when your problems get more and more abstract. So it isn't really ideal. And I think what makes the large language models that we have today sort of paradigm shift is that it enables us to represent these solutions as just natural language. And so now, instead of like looking at some complicated data structure, we can just represent the programs as natural language because we have trained these super complicated models to understand them. And the idea of this whole sort of evolutionary search guided by LLMs thing is to use the large language model to generate new solutions. So I'm going to feed these parents to the LLM as a prompt and ask it to produce a new solution. Okay. So this is sort of the general overview. And the loop for the agent itself is pretty similar. So the idea is I have some initial solution attempts. So I might have the prompts, the instructions themselves, and also a code like a Python file that solves a problem. And this can be just like a really easy sort of trivial guess. I can start pretty bare bones. Then I'll select parents according to some selection policy. Doesn't really matter. Won't go into too much detail here, but usually you do it according to fitness. So I'm going to sample solutions in proportion to their fitness, or randomly if I'm trying to do exploration or something. But the main difference is that the variation operators are going to be the large language models. So I'm going to use LLMs to act both as crossover and mutation to produce new solutions. So the mutation here, I think it's important to just give a brief comment that large language models, especially today, the way we consume them, they aren't really seedable, not easily. And so it introduces some noise to your solution. When you give us the same prompt, you won't necessarily get the same answer. So in that sense, you can think about this as being a mutation operator, but it isn't as well defined as flipping some bits in the traditional genetic programming environment. So this is just a caveat, but it's important to note. Now, and then the rest of the algorithm proceeds as same way as we did before. So we evaluate the program, execute it in a sandbox environment, compute the metrics, and repeat until we're satisfied. Okay, so where does this idea come from? A bit of history about when did people start doing this. So not unsurprisingly, this has been only been a thing for the past like 4 or 5 years. So initially, a lot of the work from the folks at Google DeepMind was really successful at generating sort of code for competitive programming and certain styles of problems using neural networks. And the specific coupling of large language models with genetic programming came with a paper called Evolution through Large Language Models. And I guess the two main sort of applications that really popularized this was fun search and evolutionary heuristics. So their idea was to, they really formulated explicitly this notion of using the evolutionary search loop to generate new solutions for certain heuristic problems. So they were trying to generate heuristics for problems like a traveling salesman problem or something like that. So more classical NP-hard optimization problems. And I guess the main reason why I'm here, what sparked my interest in this sort of area was AlphaEvolve, which was released last year by Google DeepMind. And their idea was to vastly generalize what FunSearch and EOH did. They can now sort of handle entire code bases, and they can evolve programs end to end. So they did this to a lot of really interesting examples, but AlphaEvolve remains sort of closed source. And as I previously mentioned, AlphaEvolve sort of sparked a wave of open source frameworks and projects trying to either reproduce it or sort of building on top of the idea. And here are just some examples of frameworks that you might know. So OpenEvolve, I think it's the biggest one and the most famous. There's also SyncEvolve, TetEvolve, CodeEvolve, which is the one I'm working. SkyDiscover from the guys at Berkeley. I think they're also going to give a talk later. And many other sort of interesting frameworks. And in general, has been a really sort of thriving research community. A lot of people getting interested in these things. So yeah, this is just some non-exhaustive lists of frameworks out there. They're trying to either implement sort of open source version of AlphaEvolve or do something similar with evolutionary search. So okay, now I'm going to break from the maybe the sort of introduction and overview and talk about CodeEvolve itself. So CodeEvolve is yet another framework that I started working on last year, trying to sort of implement evolutionary search guided by LLMs inspired by AlphaEvolve. But also, after doing some experiments, I also realized that this might be a really good way of maybe enhancing sort of cheaper open weight models like Qwen in comparison to the frontier proprietary models. So what's the idea of CodeEvolve? We have sort of 3 separate pillars. The first 2 ones are actually just rather sort of simple and intuitive. First thing we do is what we call the island-based genetic algorithm. And the idea is, well, we have this evolutionary search loop And instead of doing just once, we can do it like in parallel n times. And the idea is to enhance the diversity of your sort of solutions. And from time to time, you migrate solutions between the islands. So that's where the sort of whole comparison comes from. We also employed a large language model ensemble. So instead of just relying on a single model, we can sort of create, at each specific step, when we're going to try and generate a new solution, we can sample different LLMs based on either some constant weights or some dynamic rule. And the idea is, well, I might be interested in if I want to generate solutions fast for exploration, I might be interested in using sort of cheaper models. Whereas if I want to really exploit a problem and try to optimize it to the best way possible, I might be interested in using sort of a more expensive model like Gemini Pro, which is the case for AlphaEvolve. And we also introduced some operators. I'm not going to do too much detail, but the idea is that we're trying to sort of cover the whole thing about crossover and mutation directly. So we also feed to the LLMs the parent programs themselves and some other inspirations sampled according to some rules. I guess the most interesting thing is what we call meta prompting. So instead of just evolving the solutions themselves, the solutions, they have a prompt attached to them, the instructions that were used to generate them. And the philosophy here is that maybe the best prompt engineer is the model itself. So you also allow sort of like a mirror version where you treat these prompts as solutions, and you're applying also a genetic algorithm there to try to improve them. And this depth-based refinement, I won't go into too much detail, but the idea is also what we found is that if you feed the model more and more information about the process of generating the current solution, you often get more targeted changes. So the idea is if you're trying to exploit a solution, you would like to maybe look at the sort of the lineage of programs that came before it. So this is just a brief overview of CodeEvolve. And the idea is, well, I started this project trying to reproduce the results from AlphaEvolve. So naturally, I used Gemini 2.5. I think for the original paper, they actually used Gemini 2.0. But at our company, at the time, we only had access to Gemini 2.5. And I think newer versions of AlphaEvolve are using better and better versions of Gemini. And sort of as a open weight model to sort of compare and also see how far can we take these open weight models, we use Qwen pre-coder with 30 billion parameters. And I guess the main sort of thing that got me excited about this area, at first we were doing experiments with Gemini and the results were good. We managed to, match or exceed some of the results by AlphaEvolve. But it was still really expensive and sort of dependent on proprietary models. But after experimenting with Qwen, we had some really good results and overall found that, sometimes for some problems, it's not a general thing, but you can use this evolutionary search to like meaningfully enhance the capabilities of models like Qwen, which are like way, way smaller and less powerful by themselves when compared to like Gemini. So I guess that's the main thing that interests me about this field right now. Okay, so I won't go into too much detail about the benchmark problems themselves. If you're sort of familiar with this area, you already know what are sort of the traditional problems being used. But the idea of the benchmark problems for AlphaEvolve, where they were sort of benchmarking their model, it's a bunch of problems from maths, sort of optimization problems, some related to geometric packing. So you're trying to place like either circles or hexagons or other shapes inside some box, and you want to maximize or minimize a given metric. There's also some problems related to this min-max distance ratio. So I want to place some points in space and minimize some notion of like a ratio of maximum minimum distance. And there's also some inequalities related to additive combinatorics and many, many other mathematical problems. I think the original paper from AlphaEvolve, they evaluated like over 70 problems. So they're really, really sort of comprehensive. These are the most approachable ones and also the ones that when I started doing this, people were sort of most interested in. So this is just a table of the results we got. I don't want to go to dive too deep into this table, but I guess the main findings were that we were able to sort of get close to AlphaEvolve and beat it sometimes using Gemini and Qwen. So out of the 9 benchmarks we considered, we were able to sort of match it or exceed it in 5. And the other 4, we were still pretty far away. But I guess my main focus for this talk would be the first 2 rows, which is managing to use Qwen, which is a really sort of, in comparison to Gemini, a really weak model, and managing to produce better results and sort of actually advance the state of the art using open weight models. I guess that's the main thing I'll be focusing on for the next couple minutes. So I guess the main question you might be asking for anyone in this area is like, does this make sense? Like, are we doing this whole evolutionary search? Is this actually making the models more expressive? And the plots I'm showing you right now are sort of the ablation studies we made for the circumflexion problem. And the idea is that we have three curves, and the shaded region is showing like the best and the worst solutions. The y-axis is showing you some target score, so don't worry about it right now, what it means. We want to make it higher. And the x-axis is showing the number of LLM calls we made, so the number of solutions we evaluate. And so the blue curve shows the full method, so code evolve with all its components. The orange one shows like a naive evolution, so just applying the evolutionary search as it is. And the green curve shows the no evolution. I guess the main point is that, from these experiments, we did this, like the curve themselves are the mean over a number of runs. And overall, there is, of course, a gain in using the framework, both in terms of like sample efficiency and also the ability of producing state-of-the-art results. Like on the left, we can see that like both the full method and the naive evolution were able eventually to surpass the state-of-the-art, but the naive evolution took like way more LLM calls than the full method itself. And on the right side, we can also see that, in this particular scenario, the components that we introduced were actually the difference in being able to surpass the state-of-the-art. But I guess the main point from this slide in these figures is not really to advocate for my framework, but is that like naive evolution itself and this evolutionary search strategy is powerful in these scenarios. And I think these experiments sort of demonstrate that we are making something that is meaningful. And if you, instead of using this evolutionary search, you were just to prompt Quen a number of times with the same prompt and eventually hope it will produce a good answer. And I think what these experiments show that isn't really possible for some of these problems. So I do think that these experiments kind of show that there is a palpable sort of precise meaning to which these evolutionary search strategies are sort of enhancing the expressivity of these models and the power of them. And I think it's really nice to be able to produce state-of-the-art results with models like Quen, which are considered by many people sort of really weak, and people don't really use them on a daily basis when compared to like Claude or Gemini or whatever. So yeah. And also, I guess an obvious point, but I think it's still interesting to make. These two plots, don't worry too much about them, but the main thing they're showing is like a similar thing to the one before. So we're showing like the best solutions at with respect to the number of evaluated LLM solutions. But we're also plotting the cumulative API cost. So of course, this is like the API cost of the tokens. If you're using some kind of subscription, will be way, way smaller. But in practice, like if you're relying on API like we were, it makes like a huge difference. And essentially, these plots are showing that both Quen and Gemini were able to surpass the state-of-the-art eventually. And of course, Gemini requires way less LLM calls. So Gemini, in order to surpass the state-of-the-art, requires like around 400, and Quen requires like over 1,000. Or at least around 1,000. So it's like two times more LLM calls. However, in total for running this experiment for Gemini, we spent $35 in comparison to the $6 we spent for Quen. And actually, we're trying to we're running these experiments on a fixed number of epochs, but Quen actually found the solution like around like $2.50 with API cost. So it is like an order of magnitude cheaper than running Gemini. So it is not only, of course, Gemini produces a solution faster. It requires less calls, but it is way, way more expensive than Quen to an extent that it doesn't really justify for these problems. So I do think that these plots also show that there is an advantage to using Quen, if we're able to couple with this evolutionary search strategy. Okay, so moving to maybe some conclusions and some thoughts about this whole area. So I think the previous experiments and our results in general really show that there is a gain to using evolutionary search and LLMs. So just relying on zero shot isn't really a good strategy, especially if you're interested in some of these more hard problems and optimization problems and just complicated computer science problems in general. And Also a point I've been making for the past couple of minutes is that not only these strategies maybe improve any model that you use, but in particular they can sort of take cheaper models like Quen and make them perform just as well as proprietary models. And I do think that is really important, especially today, where we're seeing a bunch of startups and a bunch of companies coming, being created around sort of a wrapper around some sort of LLM. And I do think that decoupling your company from a proprietary model is always a good thing if you can do it and not lose any performance. And I do think like these sort of strategies in evolutionary search are a way of doing that. And well, yeah. And I guess the main point here is that also focusing on the architecture of the search process and on the loop itself is usually, sometimes more important than what the underlying model is. So you can make small models work with these strategies. Now, there are some limitations. I'm not going to oversell these frameworks. I guess anyone who has any experience like OpenEvolve or CodeEvolve knows that these things currently are really annoying to tune. There are a bunch of hyperparameters, and overall, it's not a really fun experience. And there have been many sort of recent papers, including from SkyDiscover, trying to fix that. And I do think we're heading in the right direction, but it's still, a lot of these systems have a lot of knobs, and it's kind of difficult to use them. And also, adapting these problems to, adapting these systems to a target problem isn't trivial, because essentially you need to have an evaluator. And for more complicated problems, this evaluator might, involve a mock of like a distributed system, or spawning a bunch of jobs or whatever. So it can be quite complicated. And in the end, for certain problems, it can involve like creating a simulation of the problem itself, which might be really hard. So this isn't, I'm comparing this with just like using a zero-shot model, just like prompting certain model on cursor to solve a problem. That for sure is going to produce a less quality solution in comparison to these frameworks. But on the other hand, it doesn't require as much tuning as these frameworks do. But also, I do think this can be fixed by integrating more sort of agentic loops and structures into the search process itself. And of course, as I've shown before, the computational cost, especially if you're relying on API calls, is not trivial. Like if you're trying to, especially for the harder problems, the circle breaking problem turns out it's quite easy for these models to beat. But other problems like the Heilbron problems or whatever, they can be quite hard, and the costs go up. So spending $10 to solve a problem might not be reasonable for most people. So that's also that. And some next steps that I think might be nice to, not only regarding evolutionary search, but like this whole field of people working on AlphaEvolve adjacent frameworks has been moving really fast, and there's been a lot of interest and a lot of really interesting work coming out lately. But I do think it would benefit for, I guess, two main things. First of all, is like standard benchmarking. So I'm talking about like a ImageNet equivalent for evolutionary discovery. There are already many attempts of doing that, but none of them, at least in my opinion, have been sort of vastly adopted. But maybe it's also a question of time. Perhaps we should just wait a couple more months and more people are going to be sort of unifying these benchmarks. But currently, if you're trying to sort of parse through the literature in this area, through the research papers, each paper has its own variation of a benchmark. So it's kind of also complicated to evaluate. And also the thing about evaluation is that, again, each paper is using a different backbone and has different hyperparameters. So it's kind of hard to reproduce and hard to know, when a comparison between two different frameworks is being fair. And also, I think that the third point is actually sort of trying to bridge the gap between the frameworks and trying to sort of be more close to each other. But I do think like events like this are sort of creating this environment for people to talk about this and get to know each other, and also to just collaborate in general. So yeah, I think that was that. If you have any questions, let me know. And also I have a QR code for the CodeEvolve GitHub if anyone's interested. Thank you.
I have a question about the size of the LLMs. Have you seen like a trend on the number of parameters as in a minimum amount of parameters where the evolution actually starts to kick in, and if you can see a law on making more parameters?
I think it's a really good question, but I don't think I'm really in the position to answer it because sort of I'm doing this project within my company's environment, and so we only have access to whichever LLM they have in their sort of platform. So unfortunately, we only have access to Qwen as sort of like an open weight alternative. But this is something that I think it's interesting to study more. But a partial answer to this is that the folks that did Theta Evolve, which I think some of them were Microsoft Research, they were sort of integrating this evolutionary search with some reinforcement learning procedures on a much smaller version of Qwen. I think they were using Qwen like with 8 billion parameters, but they were also integrating the evolutionary search and sort of fine-tuning the parameters as they go. So, Code Evolve, Open Evolve, and all these frameworks are all like fixed. I'm consuming these LLMs via API, so I'm not really training them. Theta Evolve was actually actively training as like a smaller version of Qwen. So I'm not sure at which point these models start to actually understand and be able to be successful at this loop. But I do think if you also allow yourself to fine-tune the models, maybe they don't need to be super big.
Yeah, go for it.
Thanks for the talk, Henrique. Do you know of any examples of people using these systems for developing machine learning models instead of like classical math algorithms? I know the evaluation would take a longer time, but maybe there might be some smart ways around that. But do you know of anyone doing that?
Yeah, there's actually a really nice paper from DeepMind. I think it's called Pack Evolve. It was one of their benchmarks was writing kernels for like general purpose machine learning functions in PyTorch. So they had like a huge list of different kernels, and they tried to use, they created their own version of this framework, which is kind of funny because they're a DeepMind, so you would think they would use AlphaEvolve, but they actually created a new version, which is open source. And they actually compare with like Code Evolve, ShinkoEvolve, and Open Evolve. They were quite successful, actually. But it isn't, I think in the AlphaEvolve paper, they mentioned using it to sort of optimize some of the kernels used in the training of Gemini. And there's also been I think the recent project by Henrique Parfi was trying to do sort of like a smart parameter tuning using LLMs. Yeah. So those are the examples I know. But yeah, I think I've seen a couple of examples of people working precisely on writing kernels in particular.
Nothing on like architecture.
I mean, if you consider like hyperparameter tuning of the architecture itself, like how many layers, what's the hidden dimension, etc., then yes. If you're talking about like completely new architectures or something like that, then no, I haven't seen it. But it might just be my ignorance.
Thanks.